Dear colleagues, my name is Christian Gmünder. I'm happy to present you an instrument for assessing open loop heat pumps in urban areas. The tool was developed for the canton of Zürich by a team working at Simultech company. First, I give you some introduction in a local situation that led to the development of that tool. We see here the Limmatal aquifer. Zürich is situated here, the city of Zürich, at the right side, here. In that aquifer, there are drinking water wells for about 500,000 of residents, and there are a lot of wells for construction purposes. And in 2013, when we began our project, there have been 45 open loop systems already in use. I have to say that in Canton Zürich, only big open loop systems are allowed, not small ones. And about 10 new systems are planned every year. So this situation is typical for urban areas, aquifer which is used highly. And one of the problems in an urban area is that groundwater is already warmed up by urban warming. For example, you have sewer pipes, you have buildings, you have heat distribution networks, and normally the temperature of the groundwater would be about 10 to 11 degrees, but in urban areas it's higher. It's about 13 or even 14 degrees. And if you plan a new facility, you extract water with a temperature of 13 degrees, and then you cool it down or you heat it up and you give it back with a lower or higher temperature. The Swiss legal rules say that in a distance of 100 meters to the injection well, you should have a maximum temperature difference of 3 degrees in relation to the natural state. So not to the actual state, but to the natural state. You see here in this time series graph, you see the natural temperature and plus minus 3 degrees. And you see that most of the open loop thermal heat pumps are in the upper part because you have an urban warming. So for the natural state and the future situation are not easy to know, and granting permits in this urban area is a rather difficult task. That's why the Canton of Zürich asked for a decision tool for granting permits for open loop facilities, and it should be based on a regional numerical heat transport modeling. The requirements were the model should be as exact as possible. The results should be available in a reasonable amount of time, and the tool should be robust and easy to use. I come back to these requirements later. But first, I just say something about the aquifer. It is a gravel aquifer, and it has been deposited by the rivers of Limmat and Sihl. The permeability is about 5 times 10 to the minus 3 meters per second, and at some parts the aquifer is rather shallow, and at some parts it is rather deep. The Sihl and the Limmat River are the most important boundary conditions to that aquifer, because there is a big infiltration here, and this makes the aquifer transient. Before we can build up a heat transport model, we have to have flow model. At the flow model, it is very important to have a good reproduction of the flow direction. Oops. Okay. Oops. Try to go back. I go back by that maybe. No. It is frozen. The mouse, yes, but I want to go the slide back. Sorry. No, here, yeah, back. Thank you. Yeah. Okay. For the heat transport model, we had to refine the mesh. And we have still a coarse mesh with elements of 200 meters square. And it gave us 200,000 elements. We built up a 2D and a 3D model to look at the difference. The 3D model, naturally, it takes more calculation time. And it is very sensitive to the discretization of the mesh near the surface. We had also some temperature measurements to calibrate the model, but we had to suppose and make some simplified assumption for the urban warming. This slide shows you a cross-section through the aquifer, and with a simplified open loop tool. The most important temperature exchange processes are the exchange with the rivers, and then the exchange with the atmosphere, and naturally you have the open loop system which changes the water. We had to develop some additional IFM modules for that because we used the 2D model. We made an IFM module for the heat exchange at Cauchy boundaries that makes the water temperature of the water that flows into the model, puts it to the river temperature, and the water that goes out the model to the groundwater temperature. We have used the open loop IFM module from DHI Vasi. And for the heat exchange with the atmosphere, we have made a 1D IFM module. Now I come back to the requirements. Does this model match the requirements? No. Is it exact? No, because we would need an element size of about 20 square meters to avoid numerical dispersion. And is it fast? Yeah, the actual model, yes, but if we would go down to the 20 square meters, it would be slow. And is it easy to use? I think everybody here knows FEFLOW and the 100 possibilities to make errors, so it's not really easy to use for an official at the Canton Zürich. So our conclusion was that the regional model does not match the requirements, and it is also not possible to make a local refinement because we don't know where the next facility will be planned. So the solution was a model nesting. At one side we have a regional scale model which calculates the fluid flow and the regional scale heat transport, and on the other side we have a local model which calculates the fluid flow and the heat transport in a local scale. So we can bring down the calculation time to about 1 hour. The problem is that you don't know in advance where the local model should be. So here came our new instrument. We named it GEMTool. And this instrument does automate the process of generate a local model. The tool works on a web server in our company. The tool generates a FEM file, input file for FEFLOW. Then FEFLOW is run in batch mode. And after the calculation has finished, the tool reads the results from the doc file. The client is just using that tool by using his browser. So he is used to do that. And we had, because FEFLOW does not support batch flow path calculation, we had to use our own tool. That tool is based on the continuous flow field method of Cordes. If you split the finite element model into patches, you can calculate a continuous flow field, and the entry and the exit point of flow paths through such a patch are exactly defined. We added to that tool, to that method, a water balance. If you think every flow path as an infinitesimal narrow stripe, you can make a water balance along that stripe, and you can calculate the water that is coming to the stripe. So the flow path will end if all the amount, the pumping amount that is for that flow path is finished or matched. With that tool, we can also, because we know the boundary condition at each patch, we can say how much water is getting to that well by each boundary condition. And we can calculate the flow back from the injection well to the extraction well. Before I tell you something about the user interface, I will show you the granting permits workflow the official has to do at the Canton of Zurich. First, he gets an informal request for a new facility. He now enters the facility data and the well data into the system, and he lets the system create a local model. He can start a case study. Every case study can be saved, and at the end, he can visualize the results. Based on that results, he checks the legal rules, and he can decide if the new facility is approvable or not. So after that, he informs, in any case, the applicant. If the answer is no, he can delete the case study. If the answer is yes, it is supposed that the applicant will put in a formal request for that facility. If for that formal request he has to do some additional pumping tests and so on. And if the formal request doesn't differ too much from the informal request, the official may give the permission, otherwise he has to recalculate. And if he can give the permission, he adds the facility to the database, and he lets the tool refine the regional model and recalculate the regional model. And the regional model will then give the boundary condition for the future local models. The user interface is a map with some basic GIS functionality. If the user wants to create a new case study, he has lead it through that with some screens. He has first to define the annual heat extraction, the temperature difference, and the wells. He can add the wells on the map or at the screen. And then the tool has to do its work. The tool proposes a direction and the size of the local model based on flow flow path calculation and some analytical calculations for the heat plume. And if that proposed model border likes to the official, then he can start the model creation. The model is created using the triangle code. There are refinements around the wells, and the parameters are taken from the regional model, the boundaries from the regional model, and then he starts the calculation, and he can go to drink a coffee. When simulation is finished, he can visualize the results. The calculation does always do two models, one the prevision with facility and one a reference without facility. And the natural state we take from the regional model. He can also make an automated report. So he has a paper. This report includes a facility summary, a map, just a screenshot, a flow path calculation with the amount of loopback, and it shows a time curve, and so he can decide if he wants to give the permission. So I come to the conclusions. Conclusions regarding the GEMTool. It's now become easy to make heat transport models out of a regional model. And we have used this tool already for different places in Switzerland and also in Germany. And we think that most of the GEMTool modules can also be used for local transport models as well. The conclusions for FEFLOW is that we think that similar custom-tailored applications may be important for the future market. And it is crucial for these kind of applications that they can access the FEFLOW input and output data. That's very important. And we think that maybe a kind of batch license would also be appreciated. So I come to the end. Thank you for your attention. And if there are questions, I will try to answer it.